Okay, so we're establishing how this works, not just working the problem. And so I have defined y is upward, and I'm calling the stretch of the spring from its default equilibrium, not its equilibrium in our situation, as y. Because if the spring is compressed, that's a positive y, but the force is down. That's why my force tension, as I called it, is minus ky. And so at equilibrium, we're finding the equilibrium stretch is minus mgk. That is, it's stretched downward some when it's at equilibrium. And so I'm going to define a new variable. X is equal to minus mg minus k, or minus mg over k. Oh, now I'm not thinking clearly. X not minus y hat. Yes, I know what I'm doing now. X is y naught plus y.
Why?
I'm trying to get my sign straight. Because I want force to equal 0 when x is equal to 0. And this should be the easiest thing in the world to determine what the signs are in here, and I'm not thinking very clearly. So if y is equal to y naught, then f net equals 0, right? That's what we just found up here. That was the definition of y0. Mm-hmm. And then I want my x to be equal to y naught minus y, so that when my x is positive, go ahead.
What is that? It's like plus, I can't read it, plus something f net.
I don't know where the plus is.
Right, yeah.
I think you're seeing my t and then.
Okay, gotcha.
That's then. And the reason I have, y naught minus y. So if y equals y naught, then x is 0. And the force net is 0. So substituting that definition for x, you'll see in class I won't do it this way because it's I suppose I should have done the opposite sign. Darn it. So change the sign. Okay. There, I got my sign straight. So what I've done is I have force net is minus kx, where k is how much it is moved away from its equilibrium stretch length. A whole lot of work to get there, right?
Are we gonna add x to like our coordinate, like our?
at least for part A, all we need to establish is that this is behaving as a simple harmonic oscillator, that we can have an x defined where the net force is minus kx, where x is how much is displaced from its equilibrium position.
So concept would be simple harmonic oscillator.
So because we have this, then it is indeed a simple harmonic oscillator, because that's the definition for simple harmonic oscillators, if the net force is minus kx. And so once we get that, then we use the rules we talked about yesterday that say for simple harmonic oscillator, omega is equal to square root of k over m. Remember we worked through that yesterday? Some say yes, some say no.
I was there, but I don't remember.
Maybe.
We went through, well, let me just go to the one we worked on yesterday.
Yes. Yes, we did. Yesterday was far away.
So here we had, if it's a simple harmonic oscillator, then x follows a sinusoidal pattern. I said, if you know calculus, it's very simple to say then v is omega a cosine omega t, and a is minus omega squared a sine omega t, or a is minus omega squared x.
You must not have been there.
And so using Newton's second law, a is also equal to minus k over mx. And so we could just match those up. Yeah, you may not have been there. We have omega squared is k over m, which means omega is the square root of k over m. And any strict mathematician says, oh, there are two answers. There's plus and minus, but omega is always positive. So we throw away the minus one in case there's confusion there. So that's now where we're going. Now that we have established it's a simple harmonic oscillator, this problem is a one-liner solution. It's just the square root of my k value over the mass, which was 90.0 kilograms, if I remember right. Yep. And so finding omega is very simple. I said it's a one-liner. Actually, it's a two-liner because it says, what is the frequency? How do we go from, what's the name for omega?
Mm-hmm.
It's the angular frequency now.
Oh.
And how do we go from the angular frequency to frequency?
Times theta.
The frequency, that's a little behind. The frequency is omega over 2 pi. The definition, omega is number of radians per second. Frequency is number of cycles per second. Well, how many radians are in a cycle? 2 pi. That's why. So the general way to remember this is omega is equal to 2 pi f. That is radians per second is equal to 2 pi radians per cycle times cycles per second, which may or may not show up on the screen you're looking at, but it is clearly on the screen that I'm writing on. There we go. Well, nope, that's not all of it. Try again. It should show up right here. So now that we've established what omega is and how frequency relates to omega, we just have our final answer. Frequency is equal to, and did somebody calculate this square root? I am stealing someone's calculator. And hitting quit. That's a very fast rate to be on a bungee cord. Yeah, 2 per second. But I'm pretty sure I put in the right numbers.
Question.
Yes.
All the way back up here. Why did we change to a positive X?
Where?
Because you.
Oh, okay. Scroll up a little more. I changed it because I wanted to have this have a minus sign here because I need a minus sign for a simple harmonic oscillator.
I don't see. Oh, okay.
And so that's why I went back up and changed that to a positive X and went up here and changed that to a minus X.
Oh, okay. Okay, thank you.
And forgot to change that one.
Yeah, that's why I was like, but wait. Okay, thank you.
Okay, so there we have our final answer, unless I somehow made a mistake, which, I mean, it's a non-realistic answer. You can't have 1.985 hertz and be comfortable. You're going to be but at the same time, you're not supposed to fall if you're just climbing. If you're bungee jumping, it's a different matter. Okay, so there's a part B on this. And a part C. How much would this rope stretch to break the climber's fall if he free falls 2 meters before the rope runs out of slack? Hint, use conservation of energy. Even as the old teacher, it's cool if they give me that hint because it'll save me time of thinking. Did we have to think? So, how much would this rope stretch to break the climber's fall if he falls 2 meters? So we're going to have the climber is at some place here. Let's just say he steps off he'll start here at YA. And he falls down 2 meters, YB. So he falls down 2 meters before it becomes tight. And then he's going to fall down even further until he stops. And it tells us to use conservation of energy. So let's just start right here at the top. What kind of energy does he have right here?
Right where?
At A.
Is that potential energy?
Okay, he's going to have
His maximum
potential energy is equal to mg YA. And his kinetic energy is just 0. You said he has potential. What does he have at this point?
At B? Is he half and half at that point?
Well, we don't have half and half, but we have some of each.
Okay.
So we'll have potential energy B is equal to mg YB. And kinetic energy B is equal to 1/2 mVB squared. Now, I wrote those in. I don't really care about those because that's not my final case. And when you're doing work energy, you're just comparing the starting and ending conditions. So what's his potential energy final?
0.
Well, I'm going to put mgy final, whatever that height is that I don't know. I could have defined that's 0 and be solving for YA, but it's a lot easier to say YA is 0 and solve for Y final. And well, I say it's a lot easier. It's actually fundamentally the same. It's just easier in my mind. And what's the kinetic energy final?
Oh, wait, no.
How fast is he going when he stops?
0.
Okay. So when it says break the climber's fall, it means when he stops. Not where he ends up in the end, but where he stops. So now with all of this, conservation of energy method, energy in A has to be equal to energy in B has to be equal to energy in final. I don't care about the B, like I said, so I'm just going to say don't care. And so energy A, from what we have written down, that's mgya plus 0, is equal to the final mgy final plus 0. I forgot one thing. Otherwise, you'd get, he goes back to the starting point. Sometimes I kick myself.
How does he go back to a starting point?
He doesn't. I made a mistake. I forgot the important thing here. His potential energy isn't just gravitational. Plus 1/2 K times the amount the spring has stretched squared. So how much is the bungee cord stretched? It has stretched y final minus yb. Right, because at yb, it was unstretched, but it was taut. At ya, there was slack in the rope. And so I have and that's squared. I forgot to write squared. Now looking at this, there's actually an easier way. Instead of saying ya is 0 or y final is 0, if I say yb is 0, I'm going to have my easiest solution possible. Why would it be the easiest solution if I set yb as the one that's 0?
Doesn't it stop at B?
Well, then my square doesn't have any cross terms. So set yb equals 0, which means that ya is equal to 2 meters. And then I'll put in my numbers. So I'll have mass times gravity times, and I'm still putting in ya equals mass times gravity times y final plus 1/2 K y final squared. How would you solve this for y final?
Move.
Couldn't we do, because we have, as if we were doing like Pythagorean, because you have x, and then
And it's class.
Oh shoot,
Like
sorry.
100.
Well, it's a quadratic.
Yeah, that's the word I was.
It's a quadratic. So now you solve the quadratic equation, and that gives you y final. Y final now is going to be how much it has stretched, but it doesn't. Oh, actually, it does ask how much does the rope stretch. So it turns out y final is also our answer.
Okay.
you have to go back. Once you figured out where the stopping point is, you have to go and say, now what is the amount it's stretched at this point? But setting YB equals 0, since YB was where it starts to stretch, the difference between Y final and YB is how much it's stretched.
Okay.
All right, so I'm going to finish it up after you guys leave so you can go watch it and see the last 2 minutes or whatever.
Thank you.
Yep.
Bye. Thank you.
Yes, ma'am. Okay, so I just did math there all in quiet because I'm by myself. Let's calculate really quickly. Mg over K is equal to, and of course I haven't got a calculator, so got to bring up a spreadsheet just to do this. So my mass is equal to 90 kilograms. K is equal to 1.4 times 10 to the 4th newtons per meter. And of course, G is 9.8 meters per second squared. And so mg over K is equal to 6.30 times 10 to the minus 2. And the units there are going to be newtons over newtons per meter, so meters. And so my Y final is equal to minus 0.0630 meters plus or minus the square root . And the YA, I believe we said was minus 2 meters. No, YA is 2 meters. And that's the square root of a negative value. Where do I have a sign wrong? Well, I'm glad I'm recording this. Negative. Minus 4AC. Oh, my mistake was very simple. Minus and minus makes that a plus. All right, that works out much better. And so my two answers are My answers are either 0 minus 0.569 meters or 0.443 meters. Now, looking at these, the y final, of course, is the final height. If the final height is positive, then it's above where it started to stretch, not realistic. So the final answer, the only realistic one, is the negative one. So it has to be that the amount it's stretched is 0.569, 57 centimeters, which is a reasonable distance, not very far. You're not going to go bungee jumping with this, and it's probably going to hurt a lot, but it keeps you from falling too far, getting too fast.